We are from Group G. Today, we will be present our topic on analysis of parallel algorithm.
Now, let's talk about how merging works in merge sort. In the sequential merge sort, the process of merging starts only after the list has been fully divided down into single element sublists. Once every element is isolated, the algorithm begins merging those sublists step by step until the entire list is sorted. Now, in parallel merge sort, the merging process happens differently. Here, multiple processes work together at each level of recursion to merge sublists simultaneously. For example, we have 8 elements and 8 processes. So, at level 1, 4 processes each merge of single elements and creating 4 sorted sublists of 2 elements each. At level 2, processes merge pairs of these 2 element sublists, resulting in 2 sorted sublists of 4 elements each. The last one at level 3, one processor merge the final 2 4 element sublists into one fully sorted list. Because all merging at each level happens concurrently, the overall process is much faster. This approach reduces all the total time or span needed to sort the list compared to doing it sequentially.
Let's analyze parallel algorithm performance using work and span. Work T1 is the total operation. Span T infinity is the longest dependency path. Parallelism equal to T1 over T infinity. The highest parallelism is the better. Let's look at a simple example, which is the array has been given is 38, 27, 53, 10, 12, 5, 6, and 7. Merge sort splits it into single elements, then merge them in orders. This process has multiple levels. We can analyze work and span at each level. This slide shows how the merge sort works in each level. It starts by splitting the array into small parts, then merge them step by step into bigger sorted arrays. At the top, we get the final sorted result, which is 5, 6, 7, 10, 12, 27, 38, and 43. Merge sort performance is measured using work and span, where T1 is the total effort. T1n equal to n times log n base 2. For n equal to 8, that's 24 operations. About 17 comparison is practiced. Span T infinity is the longest chain of steps. T infinity equal to log n base 2. When n equal to 8, the total is 3, the number of merge level. In short, work equal to total effort. Span is the minimum time with parallelism. Together, they show how much speed up we can get.
Amdahl's law estimate the maximum speed up of a task based on how much of it can be parallelized. It is defined by this formula, where p is the fraction that can be parallelized. 1 minus p is the sequential part and n is the numbers of processes. The speed up increases with more processes but only to a point. For example, if 18% of a program can be run in parallel using 8 cores, the maximum speed up is only around 3.33 times. Even if we imagine an unlimited number of processes, the maximum speed up would still be limited to 5 because 20% of the task must be done sequentially. This slide explains one of the key insights from Amdahl's law. Even if we keep increasing the number of processes, the part of algorithm is not parallelizable. The serial part will limit the overall speed up. For example, let's say if 18% of a program can be parallelized, that means 20% is still serial and cannot benefit from parallel execution. Using the formula speed up 1 over 1 minus p, where p is the parallel portion, we get 1 over 1 minus 0.8 equal to 5. This tells us that even if we had infinite processes, the maximum speed up would still be just 5 times faster because that 20% serial part becomes the bottleneck. So, in real applications, improving the serial portion is just as important as adding more processes. This graph illustrates how speed up behaves. If 15% of the code is parallelizable, the best speed up you can get is about 2 times. At 75%, you might reach 4 times. But even with 95% parallelizable code, the speed up hits a limit of around 20 times. This shows that the sequential portion becomes the bottleneck and limits how much we can scale performance. So let's take a look at span, also known as the critical path. In a parallel algorithm, the critical path is the longest sequence of tasks that must be performed one after another. This means no matter how many processes we have, we still need to follow this path step by step. So the execution time of the whole program is limited by the time taken to complete this critical path. Let's take an example. Suppose the total work is 100 computation units and the span is 30 computation units. Using the formula, maximum speed up equals 100 divided by 30. This gives us approximately 3.33 times speed up. So, even with unlimited processes, the best speed up we can get is only 3.33 times because of the sequential parts of the algorithm. Why it matters? This shows us a very important concept. Adding more processes does not always lead to higher performance. The critical path acts as bottleneck, a part of the system that limits how much faster we can go. So, in designing a parallel algorithm, it is important to reduce the span as much as possible to improve scalability and performance. Let's look at the updated formula to reflect real-world conditions. Practical speed up equals 1 divided by the sum of the parallel portion over n processes and the overhead. For example, if 18% of a task is parallelized and we use 16 processes with a 10% synchronization delay, the speed up is approximately 2.86, much lower than the ideal case. This shows how synchronization penalties reduce expected performance gains. In conclusion, this study shows that parallel merge sort can significantly improve execution time through effective task decomposition and span reduction. However, speed up is limited by serial portions of the algorithm, as explained by Amdahl's law. Real-world factors like synchronization and load imbalance also impact performance. Overall, designing efficient parallel algorithms requires both strong theoretical understanding and practical implementation strategies.